Guys, Mr. Gagnon here. Again, best played at 1.25 speed from YouTube. Okay, so what we've got going on is a situation where we need to tie all this stuff together. Now, I'm going to tie it together. It will actually be called Tie It Together. Okay, tie it together. Now, I'm going to give you some items. Okay, I'm going to take a few numbers from our charts. Okay, what I'm going to say is that I've got ice on ice. So we've got ice on ice. Okay, so here's the problem. This is ice. This is ice. Okay, two surfaces that are pretty slippery, and I know that I can get some values for ice on that page 120, and I'm going to apply some forces to my ice. First of all, I'm going to say that the mass of the ice is 10 kilograms. Okay. I'm also going to say that I'm going to apply a force of 20 newtons. Okay, I'm also going to draw in our arrows to represent, the force of friction. We don't know static or kinetic yet. I'm also going to add in the normal force, and I'm going to add in my weight. Okay, so first things first, the ice is not moving. Okay, what I'd like you to do is to be able to get the force of friction static of the ice if it's not moving. Okay, well, first steps first. Ice isn't moving, it's going to be static. I need to know what the mu value of static on ice is. So if I look up at my chart, okay, ice on ice, static is 0.1. Now, just because I have it in front of me, I'm going to put the kinetic value too, which we know is going to be less, and actually it's 0.03. Okay, so my first question was to find out the static friction here. Okay, so let's see. We know that the static friction equals the mu sub s times the normal force. Okay, now here's the issue. I only gave you the mass. Okay, so let's first of all say, well, this mass has to have a weight. So the weight we know is mass times gravity. The mass of the ice is 10 kilograms. Gravity is negative 9.8. So I got the weight as negative 98 newtons. So I can put that down here. Now, because the weight and the normal force are equivalent in size, not direction, but size, I know that the normal force is going to be 98 newtons. Okay, and I put this little strike through here to show that they're equal. So I'm going to also put in that the normal force is 98 newtons up. So look what I have here. I've got the force of friction is what I'm looking for, is equal to mu sub s times the normal force. Okay, let's do it. Mu sub s was 0.1. The normal force is 98 newtons. So it turns out that the static frictional force is 0.1 times 98, or 9.8 newtons. Now, here's the sticky point. Where I start looking at the frictional force, I can put that in here, 9.8 newtons. But I know that the frictional force opposes any motion or any motion here. So let me break this down for you a little bit more. Now, because the frictional force is 9.8 pulling back, and that applied force is 20, we just arbitrarily gave it that number. I'll write this question, does the applied force break friction? Well, look, applied is 20, frictional force is 9.8. Yeah, it does. Answer: yes. Now, that's all you need to know in this first part, that the applied force definitely breaks friction. But once it breaks friction, what happens to the ice? You got it. It moves. It starts to move. So because it starts to move now, okay, if answer is yes, okay, then it moves. Now it becomes very helpful for us to calculate the kinetic friction between the two surfaces. We said that the mu value was 0.03 right there, and the normal force is still 98 newtons. And when I calculate these things out together, the kinetic friction is now 2.94 newtons, the opposite direction. So notice what I have up here. I got my 9.8 pulling, but now once this breaks, now I have to say, well, hey, now the ice is moving. I take this 9.8 number, and I'm actually drawing a picture of a trash can, because I take that and trash it. It's gone. Bye-bye. Frictional force of static is now gone because it's not static anymore. It's moving. So now that the frictional force of static is trashed, the only thing I have left pulling backwards is my frictional force of kinetic, which is 2.94 newtons. Now, the problem is not done, because now I've got to go through and say, well, okay, now I've got kinetic friction working against my applied force. So let's draw a little free body diagram based on that. 20 to the right, 2.94 to the left. So look, net force in this entire system, now that it's moving, 20 to the right, 2.94 to the left. So getting the calculator out, 20 minus 2.94, the net force is equivalent to 17.06 newtons to the right. So if I were to draw that, it'd look kind of like this. Okay? So now I've calculated the net force of this thing while it's moving. Now notice all the working pieces here. First of all, I had to see if my applied force were able to break friction. And because this was only 9.8 to the left, it did break friction. So does the applied force break friction? If yes, then now it's moving. So if yes, now it's moving. Because now it's moving, the frictional force becomes less, and we calculate the frictional force. Now, I've got my frictional force to the left, my applied to the right, and I can now find the net force here. Yes, we're going to take it that next step. Okay, now find the acceleration of the block. Okay, find the acceleration of the block. Well, we know that A is net force over mass. Okay, so we've got a net force of 17.06 newtons. We've got a mass, 10 kilograms. Okay, so 17.06 over 10, the acceleration is 1.7 meters per second squared. Okay, and that actually ties up this whole problem. Again, long-winded, but you're going to have to maybe go back and look at the problem again. Quick recap. I gave you a mass. I gave you an applied force. Okay, I asked you to first find the static frictional force, which you did. And then you said, well, because 20 beat that, it now moves. And then I drew a trash can to show that you trash the static force once it's moving, because it's not static force anymore, it's kinetic force. So once we know that it breaks friction, the answer is yes, it breaks friction. Then we calculate the kinetic force of friction. We apply it to a new free body diagram, and then we calculate the net force. After the net force is calculated, then we can calculate the acceleration. All right?